Hello and welcome to the first lecture video for AP Chemistry. This is for Chapter 1, Matter and Measurement. It's our introductory chapter, and this lecture will cover the first part, the matter section of this chapter. Most of this will be some review, and then there'll be some things that are kind of new to you guys, so whatever you feel you need to take notes on, I encourage. You can always rewind and go back and use this how you wish. All right, first thing, study of chemistry. So this class, we will study chemistry. We'll study matter. That is a huge piece that we will study. And matter is anything in our universe, all the material of the universe. And it's anything that has mass and occupies space. So things that have mass and volume are considered matter. An example of something that is not matter, because usually people ask, is something like energy. Energy does not have mass. It does not occupy space. It is transferred between matter, but is not a substance on its own. So, matter has properties, and these properties are going to allow us to identify it and distinguish it from other materials. So we can look at some things like its color or its malleability or different things like that, all of its properties to help identify things. In our world, there are 92 naturally occurring elements that are combined in hundreds of thousands of ways that make up everything in the world around us. So elements 1 through 92 are naturally occurring. Anything after that on our periodic table, the one you have for this class goes up to element 111. There are more after that. I believe we found 115 at least. The ones after 92 are all man-made, which is pretty cool. We've made them in a lab. We don't know a lot about them, but we have made them. So matter is made of atoms. Atoms are our smallest building blocks in the world. We do not have anything smaller that retains its own properties. So we do have things like our protons, neutrons, and electrons that make up the atoms, but they themselves do not make specific types of matter. You have to build those into an atom before you have anything you can do stuff with. So atoms combine to form molecules. And when you make a molecule, it has brand new properties. In our textbook, you will see, you should open up your textbook soon, like now. And if you flip to chapter 1, you're going to see that you'll see some pictures of atoms and molecules. They're going to be represented by these small colored spheres, and the spheres are going to represent different elements. What's important to know is that in the back of your text, there is a key. The very back cover, there's a key for the color chart, the color coding for this. We will be answering questions and using these a lot, so referring to that key and knowing where it is important. So atoms combine to form molecules, and they have new properties. And we're talking about lots about properties in this chapter. All right, so why do we study chemistry? Who cares? I, of course, care because it's fabulous. But chemistry is involved in many aspects of our daily lives, and it's at the heart of a lot of matters that are of public concern. Healthcare, improvement in our healthcare is a huge part of chemistry. Conservation of our natural resources, changes in our environment, protection of our environment, all of those are chemistry. The new developments that we have in solar technology has to do with chemistry. Providing our daily food needs, our shelter needs, our clothing needs, all of that deals with chemistry. Chemistry also provides advancements in a lot of areas. So things like pharmaceuticals, when we go to the doctor and we get prescribed something, those pharmaceutical substances, they're helping us. Chemists researched it and were able to come up with these things. Food production improvements through making pesticides and new fertilizers, making plastics and new materials like carbon nanofibers. Those things are amazing. All of these substances would be nothing without chemistry. I mean, imagine our world if we didn't have plastic. It would be completely different than what we know it to be now. So, studying chemistry will enhance your understanding of the world around you in a new way and provide insights to things that you have never thought of. So you guys have all taken a first year chemistry class at this point, and you're ready to learn more. So this is going to give you that insight into some brand new stuff that you've never even thought of. Pretty awesome. So here's another breakdown for chemistry. If you look at the front cover of your textbook, it is called Chemistry, the Central Science, and this is a beautiful representation of that. So chemistry influences all of the other types of sciences. If we start at the top up there, we've got biology. The way our cells react, the way that lipid bilayers and all of those things work, microbiology, all of those things, genetics, that is all based in chemistry. We talk about plant sciences and how plants work. That is based in chemistry. Environmental science, how our environment reacts to changes in carbon and in CO2 levels and things in our atmosphere. Chemistry. Geology, study of rocks and minerals. Minerals are made of molecules, which are made of atoms, which is matter and which is chemistry. Astronomy, actually a lot of advances and things we know about astronomy have come from chemistry, because we're able to use amazing telescopes to look at other planets and look at their atmospheres and analyze those atmospheres using chemistry and what we know of the chemicals to figure out what those atmospheres are made of. Pretty cool. And when we get into physics, we start talking about the quantum level, so we start talking about below the atomic level and what those protons and neutrons and electrons are made of and how they interact and how that all works. That's all quantum mechanics, which lends itself into nuclear physics and nuclear chemistry, which is, of course, nuclear power, all of those things. And we get into things like body imaging, so MRI machines, which is magnetic resonance imaging, MRI. Technically not actually the name, they changed that. It's actually NMR, which is nuclear magnetic resonance, but nuclear kind of freaks people out, so they changed it to MRI for the hospitals. But that's the same stuff. It's a way of using a radioactive substance to take pictures of what's inside of us so we can see and be able to diagnose things. So of course that lends itself to medicine, nutrition, and then of course into biochemistry or molecular biology, genetic engineering. All of it relates to chemistry. So chemistry really ties in our sciences. We have this big umbrella of a science, and we have all of these different areas that are influenced by each other and by chemistry. So this study of matter. The first thing we can look at when we study matter is our states of matter. We break down the states of matter into the three basic ones: solids, liquids, and gases. Yes, there are more. We have plasma. No, we will not really discuss plasma that much in this class because it's really not something that we can do in a general chemistry class. We don't have ways of studying plasma. Even gases are a little bit difficult sometimes. So we're going to just focus in on these. So solids, definite shape and volume, meaning you can look at their shape, and that shape, maybe you can change it, but it will have a shape. It will have a volume. It will take up space. And then a piece that we talk about with solids, liquids, and gases is their ability to be compressed, meaning that how much can we push those atoms together more. When we're talking about a solid, the atoms are pretty close together already, so we can't really compress them very much anymore. So they cannot be compressed to any large extent. We can't really compress solids that much together anymore. Liquids are going to have a distinct volume. So you can measure a liquid volume very easily. We do that in baking all the time. But they will take the shape of its container because of the ability of a liquid to flow. So we know if we have water in a cup, it's going to take the shape of the cup. Once you pour it out of the cup, it's not going to be the shape of a cup anymore. It would be awesome if it was, but it's not. So because of its ability to flow, it will just flow out and maybe cover your table or whatever you're pouring it into. Now, liquids, of course, they do want a shape, and if they didn't have gravity affecting them, if you were to look at pictures of or videos of the astronauts on the space station, and they have droplets of water, those water droplets will form spheres. And the reason they do that is because all the molecules of water want to stick to each other, and the easiest shape for them to make to do that is a sphere. So those are our liquids. Oh, you'll also notice that we have some symbols, S, L, and G for solid, liquid, gas. We will be using those in our chemical reactions to show and denote what state of matter a chemical is in. So gases, sometimes referred to as a vapor, they do not have a fixed volume or shape. So they're like the opposite of a solid. They don't have a volume or shape. They will conform to the volume and shape of their container. The reason is because gases are these molecules or atoms that are completely separate from each other and are moving around a lot. So if we have the shape and volume of a star-shaped balloon, our gas is going to be in that shape. If we have the shape and volume of a giant hot air balloon, then our gas is going to take the shape of that giant hot air balloon. It just depends on its container. Gases can be compressed to occupy a smaller volume because there is so much space between all the atoms. We can smush them together and take up less volume, or they can be spread out to occupy a large volume. And these states of matter are just our fundamental, our base level way of describing matter. We can always describe the state of matter sometime. All right. Kind of continuing on this, let's just look at water. So water, I'm using a little pen here so we can check some of this stuff out. Let's start with gas because it's kind of our, we're going to work backwards here. So gas, of course, in this iceberg picture up here, it's represented by our sky. We have gaseous water, our clouds in the sky made of water molecules. These are individual water molecules. Ooh, that's weird. I don't know why it's drawing way over there. Anyway, our water molecules are an oxygen in red and our hydrogens in white. And there we go. Apparently if I do that, it'll work. So there's our water molecule. When we're a gas, they are completely separated from each other. Okay. When we're a gas, they're completely separated from each other, and they move really quickly, and we have lots of space between them, so that's where we get that compressibility. When the substance is a liquid, to the left, we see that our water molecules are closer together. They're going to slow down, move slower, be closer to each other. And then if we go further to the left in the iceberg, those little zoom in shots, we get our solid. What's special is when we get to the solid part is that we're creating some bonds between our substances. So if you look, our arrow that goes from our solid over to the top right hand side where we have our picture, it talks about hydrogen bonds in ice. So we have our water molecules sitting there, and they're all connected with these red dotted lines, and those are called hydrogen bonds. So this is a weak bond that's formed between molecules, and it kind of holds them together. It gives them a sort of stickiness to each other. Well, in water, when we have those hydrogen bonds and those hydrogen bonds are all stuck together, we form ice. It gives ice that rigid structure. When we melt ice into water, we break down those hydrogen bonds. We're just breaking the water molecules from each other. We're not actually breaking the water molecule itself. It does not change into oxygen and hydrogen when you melt or boil water. So if we look down at the bottom right, we have that really rigid structure on the left, which is our ice, and then this kind of smushed together version of that looks kind of like the molecules are really unorganized, and that's our liquid. Our ice is a little bit bigger of a structure than our water is, and that's why ice, when you like put a water bottle in the freezer, it will expand. The water seems to expand and sometimes can break the container because it's forming those hydrogen bonds and getting this rigid structure. When it melts again, it takes up a little bit less space, and because we don't have that rigid structure. So, classifications of matter. Solid, liquid, gas, matter. One way of describing. All right, more ways of describing matter. When we talk about matter, we're either going to be talking about pure substances or a mixture of substances. A pure substance is any type of matter that has distinct properties. So it has its very own properties, and it's a distinct composition, meaning we know what it's made of, and it doesn't change from one sample to the next. So an example of that might be an element. So this is one category of a pure substance. It's made of one type of atom. If I'm talking about chlorine, it's just made of chlorine atoms. It's going to be the same from sample to sample. It'll all have the same properties. If I'm talking about a compound, which is made of two or more elements, and those elements are bonded together, that will still be the same from one sample to the next. So if I have water, H2O, it's always going to be H2O. It's going to have the same properties for every water molecule, and it's going to be the same matter, same atoms that make every water molecule. So those are our pure substances. And then when we combine different compounds or different elements together and they're just hanging out with each other, they're not actually chemically reacted, we can make a mixture. So a mixture is a combination of two or more substances in which each substance retains its chemical identity. The easiest example of this would be something like salt water. So when we have, oh my goodness, okay, sorry. Apparently that's not going to work. All right. Well, when we have sodium and chlorine, sodium chloride, we make table salt. And if we put some salt into water, we can make salt water. Well, it's still salt and it's still water. We haven't made a new substance. There isn't some large saltwater molecule that forms. They're just salt and water hanging out together. So it retains their chemical identity. But it might have some new props to it. Okay, few things we need to remember about our substances. First thing, elements have symbols that either have one or two letters. Our first letter is always capitalized. The second letter, if it has two, is never capitalized. Many of our symbols are derived from their English names, like iron, are from their English names. So if you look at this table, we have the first two columns. We have our carbon, hydrogen, all that stuff, all these. All of those are from their English names. So their symbol is coming from their English names. Chlorine is Cl. It kind of makes sense. But when we get to things like copper, its English name is copper, but its symbol, Cu, comes from its foreign name, which is cuprum. So a lot of our substances that we're like, why doesn't the symbol match the substance's name? It's because it's coming from its foreign name. For instance, tin. Like, tin symbol is SN. That doesn't really make much sense, but it comes from stannum, which is its foreign name. So it kind of makes more sense when you hear it like that. Another thing to remember, our periodic table that we use in this class and will be given on your AP test does not have the names of our elements. It only has the symbols. So if you're looking at the periodic table and you're looking for mercury and you don't know that mercury's symbol is Hg, you're going to be spending 20 minutes on your AP test looking for mercury. It'll be bad. So we're going to work on learning some of these symbols, especially through the use of them. You'll get so used to using many of these symbols that it'll be like second nature. And we'll do some little quizzes through the year, just quizzing each other on our element symbols. Compounds. Compounds are formed through the chemical reaction, or through a chemical reaction. Like when hydrogen is burned in oxygen gas, we can form water. Compounds have distinct names and ways of writing their symbols, and we're going to review this. So, for instance, we don't just call sodium and chlorine when they're combined sodium chlorine. We call it sodium chloride, and that tells us something about that substance, and we will review how we write that and where that name comes from. Compounds always have the same composition. So water is always H2O. We have two laws that represent that. One is called the law of constant composition, meaning that its composition, what it's made of, is constant, it stays the same. Or we say the law of definite proportions, meaning that water is always hydrogen and oxygen, but it's also proportion. So there are always two hydrogens for every one oxygen. So that law, it has definite proportions to it. Just a couple things about elements and compounds. Mixtures. Most matter we encounter in our world is a mixture. Each substance in a mixture retains its identity and its properties. So like we were talking about salt and water. And mixtures can vary in their composition. So an example, if I make a cup of coffee, which I love, and I put cream and sugar in it, let's see, a cup of coffee with cream and sugar has the same substances, but each person that makes their cup of coffee is going to vary the amount of each substance in it. So I may put a ton of cream and a little bit of sugar, and you may put no sugar, or like a ton of sugar and no cream, or a tiny bit of coffee and it's all cream. And we have a million different ways we can make this cup of coffee. So mixtures vary in their composition. Mixtures don't always have the same composition throughout them, and their properties and appearance can change throughout a mixture. For example, if we look at a rock, like a sedimentary rock has layers in it, they're going to be made of mixtures of minerals, and they're going to vary in their texture and appearance and all those things. So they're not uniform, and when they're not uniform, we call them a heterogeneous mixture. Hetero meaning different, so it's made of different pieces, and we can see those pieces. When a mixture is uniform, like the air around us, it's very uniform in its composition, it's called a homogeneous mixture, or homogeneous. When something is homogeneous or homogeneous, we say that they are called solutions. This should be a review from last semester. Although in our world around us, we may say something is a solution, and we often think of it as a liquid. Solutions can be solids, liquids, or gases. So the air around us is a solution of gases. But we can also have solutions made of liquids or solids, or combinations of any of them. So I could put salt in water and make a saltwater solution. It's a solid and a liquid. All right, so to clarify, if we're talking about a pure substance, we can have things, atoms of an element. We can also have molecules of an element. So we can have two of these blue spheres representing nitrogen in this case, and they can be stuck together because nitrogen is more stable when it's paired with itself. So we have molecules of that element. These are both referred to as elements. When we have two different atoms, two or more atoms combined chemically, we call them a compound. So these are molecules of different compounds. They have at least two kinds of atoms. When we have a mixture of elements and a compound, we have something like this, we get mixtures. So we have elements by themselves, elements together in a molecule, or we have compounds. Any type of, or mixtures can be a couple different compounds, it could be a bunch of elements, it could be any mixture. Lots of options. So elements, compounds, mixtures. Okay, this is just a little summary to kind of break down how we decide what category matter falls into. So the first thing is it homogeneous or heterogeneous? So is it uniform? If it's not uniform, it's going to be a heterogeneous mixture. If it is uniform, then we can break it down a little bit more. It's homogeneous, meaning it's the same throughout. Now, it says, does it have a variable composition? Meaning, is it made of different pieces? Do different pieces make up that form of matter? If we say yes, then you're making a mixture. You're making that homogeneous mixture, or a solution, another term, so salt water. If it does not, then we are talking about a pure substance, and that pure substance can fall into two categories. If it can be separated into smaller substances, if it can be, yes, it can be, then it's a compound. If it cannot be separated into smaller substances, then we're talking about elements. So when you can separate it, you're separating the compound into its different elements. The way of breaking this down. A couple other things. So we're going to talk about some physical chemical properties and changes, and then got one more part after that. So physical properties of matter. So physical properties are things that can be observed or measured without changing the identity or the composition of the substance. So a physical property, it falls into two categories. So let's talk about those two categories. Intensive properties mean they depend on the type of substance we're dealing with, and it can be used to identify it. So density. Every substance in the world has its own density. So we can use that property to identify that substance, and it's going to depend on the type of substance. Extensive properties are going to depend on the amount of substance present in the sample. So our volume would be an extensive property. If you have a little bit of something versus a lot of it, its volume changes depending on how much you have of it. But if you have 10 milliliters of water and 10 milliliters of oil, there's still 10 milliliters. It's still the same volume. So it doesn't matter what kind of substance, it just depends on the amount. So those are both physical properties. We can observe those things, we can measure those things. They all fall under that kind of umbrella of physical properties. If we're talking about chemical properties, then we use chemical properties to describe the way a substance changes or reacts to form a new substance. That's the key there. So it's changing to form a new substance. The way we distinguish a chemical property is, I like to say, can we put it into this sentence? The ability to blank. So something's ability to burn, we say it's flammable. So that's a chemical property. It's flammable. Doesn't mean it's actually burning right now. It just has the ability to. It can burn. Paper is flammable. That's a chemical property. So we'll be explaining some of that in class. All right, changes in matter. So physical and chemical changes. When you're talking about a physical change, it's when substance undergoes a change in its physical appearance, but not in its composition. So not what it's made of, just in what it looks like. So going from solid to liquid, liquid to gas, gas to liquid, liquid to solid. Any of the state changes would be physical changes. When we're talking about a chemical change, it's a chemical reaction. If you can write it as a chemical reaction, then it's a chemical change, and by definition. So when a substance is transformed into a chemically different substance, so if you take hydrogen gas and you take oxygen gas and you burn them to form water molecules, you have gone through a chemical change. It's no longer hydrogen and oxygen, it's now water. And it's a chemically different substance. Has new properties, new composition. Back kind of looks like the openings that are on here for our guidance. Anyway, and we again attach a rubber hose to it. So that rubber hose is then connected to a vacuum, and you turn on the vacuum and it sucks air through that hose. And of course, if that hose is connected and everything's closed up in this container, it's going to pull air in through this filter at the top. Well, if you put a little piece of filter, a little disc of filter paper in here, and you pour your substance directly onto that, like this one's being poured, the yellow substance, we get this little pile of our solid up here, and the liquid will be pulled into the container below. This is a little more efficient because you're actually sucking the liquid through and you're not just passively allowing it to drip. So it's a little nicer when you have vacuum filtration. We don't have it at our school, sadly. All right, last slide, I swear. Okay, our last way of separating mixtures is called chromatography, and it depends on the ability of a substance to adhere to the surface of a solid. So in the setup, we have a container, and in it we have a solution. The solutions vary depending on what type of chromatography you're doing. And then we have a piece of chromatography paper or filter paper. And that paper is able to soak up that solution very easily. And as that solution soaks into the filter paper, it's going to move up. And we get this kind of line where our liquid is traveling. So we have a dot of just black, what's it called? Ink on here, and we can see that it separates out into a bunch of colors by this process of chromatography. We get the pinkish colors, pinkish purple, down at the bottom because they're going to be larger molecules. They're going to be heavier and stick to the paper more. And then we go up, and as we go up, these would be, the blue at the top would be lighter molecules, smaller molecules, and they probably aren't sticking to that paper as much because of their properties. So we can separate out the substance based on its ability to stick to the surface. Now you could keep going with this. This could separate out into each of the different colors very easily if it was allowed to keep going. And you can actually cut up the filter paper and extract that substance out of it and do all kinds of things. So this is actually one way that they are able to separate substances like this. Pretty cool. All right.